Okay, so as a recap, we talked about last week was cubic equations of state. And so we had a PV diagram, and we plotted out, well, we drew out an isotherm, which means that we followed a path of constant temperature. And they look something like this. This would be for the van der Waals equation of state. So in order to plot this, we have to assume a constant temperature, plug in a value for the specific volume, and that gives us a value for the pressure. Now you'll have to be plotting this out in the next homework. This region can actually be kind of hard to find. If you're plotting out for the first time, you don't know where to look. So I recommend doing a log-log plot on the homework when you have to plot this out. It'll make it easier for you to see small differences. Because as a good rule of thumb, the density of a liquid is about 1,000 times different from the density of a gas. So if you do linear spaced points, right? Let's say you do 0.001 up here or something like that. Are you going to be doing, 1.001, 1.002? Now you'll probably want to do logarithmically spaced points. So for any particular pressure, you're going to have 3 roots to this equation. Two of these are stable, and one in the middle is unstable. So that this is your vapor, and this is your liquid. So with the equilibrium criteria, for 2 phases to be in equilibrium, we have to have that T of the vapor, put this in a different color, and P of the vapor have to be equal to T of the liquid and P of the liquid. And we've satisfied that graphically from this line here. We drew a horizontal line at constant pressure here, and we'll know that this is the vapor pressure if we've drawn it correctly. And we've drawn a constant temperature line, which is our curvy isotherm. Now the last criteria of phase equilibrium is that these areas have to be the same. And of course, I did not do a very good job drawing it. So when the areas cancel out, that means that the Gibbs of the liquid is equal to the Gibbs of the vapor. And under these circumstances, if I had drawn this vapor pressure line a bit better, and these areas would have canceled out, we would have had our vapor pressure for whatever this equation of state was. In this case, it could be the van der Waals. Okay, but there's another approach that we can take, and that is we could use the fugacity. So for now, the fugacity is just sort of a different concept that we can use to calculate phase equilibrium. For multi-component phase equilibrium, the fugacity becomes almost necessary. That has to do with the discontinuity and the entropy. But we will talk about that next week when we get to it. So, we will talk about fugacity. So if we take our chemical equilibrium criteria, that the Gibbs of a liquid at some temperature and pressure has to be equal to the Gibbs of the vapor at some temperature and pressure. We can also write that the change in Gibbs free energy following some path of T and P is given by this expression here. And this is what we use as the starting point for balancing out the areas using that cubic equation state, if you guys recall from last week. So for our derivation, we're going to do two things. We're going to assume two things. One, we're following along a path of constant temperature. And two, we have some equation of state that we can use to manipulate pressure, volume, and temperature. So from these assumptions here, we're going to say, we're going to choose a follow for a pressure change going from P1 to P2, where dt is equal to 0. We have just integrated the expression above.
Does dt equal 0 or?
Oh, dt equals 0. Yeah, didn't close the parentheses. Okay, so this is for a real fluid. We've made no assumptions right now. Now we can do the same thing for an ideal gas. The only thing that we've done here is we've just substituted in the ideal gas law in the place of that specific volume term. Right, and this is the same approach that we're going to take throughout whenever we evaluate any of these complex functions. Right, we just have to grab an equation of state, substitute it in, and work out the math. So most all of thermo is really just plug and chug type problems. All of the derivations we're basically handling in class. So everything else outside of class with numbers should just be plug and chug. But the math is a little bit more complex than a standard plug and chug type problem. That's a little bit of calculus is involved. So if I call this expression A and I call this expression B, yes, question? Oh, I'm sorry, yes. Should be the same thing. dB. So what we're going to do is we're going to subtract B from A. And this is what we call the Gibbs departure function. So the departure function, there's enthalpy departure functions, entropy. So a departure function is basically just the real fluid property minus the ideal fluid property.
Like the excess properties?
Excess, no, different. So excess properties have to go with multi-component systems. So excess is the deviation from the real fluid mixture property and the ideal mixture fluid property. The departure function is for a single real component minus the ideal gas. So obviously after we wrap up one component multi-phase, the next step is going to be multi-component, multi-phase. And then we'll talk about excess properties a lot. Okay, so the Gibbs departure function then we can put an underbar on all these to make them specific properties. So all we've done is we've taken the Gibbs of the real fluid and we subtracted the Gibbs of the ideal gas. If you recall, we accomplished that just by substituting in the ideal gas law in the equation that we started with. Okay, so the last thing that we need to do to define fugacity is we're going to say if P1 is equal to 0, that means we're dealing with an ideal gas. So if that's the case, then this term here goes to 0. Because at pressure equals 0, all fluids behave like ideal fluids. There's no interactions. They're just that one molecule suspended in an infinite sea of nothingness. So there's nothing to interact with itself. So our equation simplifies to Gibbs of some temperature and pressure, which is the pressure has to be, of course, greater than 0. And at this point, we've effectively defined the fugacity, but they like to write it a little bit differently. So what we're going to do is we're going to take this departure function here, and we're just going to scale it, and that'll be our fugacity definition. So we define fugacity as effectively just the scaled departure Gibbs function. And we can also write this lots of fun different forms we can write this as, and one other form here. And we can also define the fugacity coefficient as equal to the fugacity divided by the pressure. So this bottom equation is actually the most useful of all of them, because our equations of state are generally all pressure explicit, which means that there is no way that we can really and easily rearrange the van der Waals equation or any other equations of state, for example, to get it as a v as a function of something else that we can easily substitute and integrate. But instead, the van der Waals equation, right, we cannot rearrange this equation to make it trivially easy to write it as v as a function of something else. But it's already in a pressure form. So we can just simply substitute this into here and then go about our integration process. Z, if you recall, is equal to PV over RT. So at any point, if you need to know the V root, for example, if you're trying to solve vapor-liquid equilibrium, you can also conversely just calculate the Z. Now, how we get this bottom equation here is through a variable transformation. Now, we don't have to go through this exactly. I'll just show you how it starts out. So if you take dPV, this will be equal to P dV plus V dP. And the trick to doing all of this is that you can relate this here to dz, right? Because the z has the PV contained within it. So that's why whenever you look at any of these equations in thermo, and anytime you typically see one of these dV terms here, it'll always be accompanied by these z's. Because that's the easiest way to transfer out from P to V space. But it's much cleaner to work. I mean, this equation here, defining fugacity is obviously much cleaner and easier to sort of look at. But in terms of actually practically solving problems, the bottom equation here is the one that you'll actually be using. And that is really just due to the limitations of how we have developed the cubic equations of state. So it's really just all a practical reasoning for all this. Okay. So one more step and we can go back to our phase equilibrium problems. Okay, now we've defined this function fugacity, and I've mentioned it's a useful term for phase equilibrium calculations. In fact, it's a necessary term for multi-component phase equilibrium problems. But can we use it at all, is the real question. So in our equilibrium criteria, we have thermal equilibrium. Makes sense. Phase 1 has to be same temperature as phase 2. Mechanical equilibrium, nothing can be moving, right? If one fluid has a higher pressure than the other, it's going to be physically pushing it. So nothing can be moving, nothing can be diffusing, nothing can be happening. And lastly, the Gibbs free energy across the phases has to be equal to constant. So if we take the fugacity definition and we unpack it, right, the fugacity is defined as a scaled Gibbs departure function. So all we have to do is unscale it. So the Gibbs is equal to the Gibbs of the ideal gas at some temperature and pressure. All we've done is rearrange the definition of fugacity. But how we defined it is the Gibbs was moved over to the left-hand side of the equation, divided it by RT, and then took the exponent of it, and then times it by pressure. A lot of manipulations, but just algebraic. Okay, so if we apply this equation to our chemical equilibrium criteria, So the ideal gas Gibbs is the same, because we don't care if it's a vapor or a liquid or a solid. We're saying, well, that's the ideal gas Gibbs. So it's saying it's gas. So those are obviously the same. Temperature 1 is equal to temperature 2. R is equal to R always. Pressure 1 is equal to pressure 2. And then we just get rid of the logarithms, and fugacity of phase 1 is equal to the fugacity of phase 2. Okay, so I'll give a really quick preview of why fugacity actually is an important term to know. At this point right here, it's really just a convenience mathematical substitution. But when it comes to multi-component equilibrium, it becomes very important. So when we talk about multi-component equilibrium, it's actually this G over bar of I in phase 1 is equal to G over bar of I in phase 2. Now what this over bar means, it basically means property in the mixture. So that the total Gibbs of a particular mixture is equal to the summation of the mole fractions times by sort of how much each individual component brings to the party. Now we can write the Gibbs over bar breaking it down into how much enthalpy and entropy comes to the party. Now the problem is, I am to plot out the entropy that a particular component brings to a mixture as a function of its mole fraction. It looks like this. In this region right here, has a negative infinity slope. Even in the ideal case, you always have this negative infinity. And that gives us a bit of a heartache when we're trying to do math. So instead, if we take the Gibbs and minus the Gibbs ideal gas, we get rid of that negative infinity slope. So that's the reason why we have excess properties. The reason why we have excess properties is because we don't want to concern ourselves with these sort of funky, weird shapes, because these are always going to exist even in ideal gas mixtures, right? Ideal gas mixtures. So even in the simplest form of a mixture, we have a really complex nonlinear function that has a discontinuity at a region that we really kind of care about. So the excess property is a convenience so that we can avoid having these complex nonlinear functions. So instead of saying, okay, what is the actual mixture property? No, we don't care. It's much easier for us to say, what is the deviation from the ideal mixture case? Same thing like in single component phase equilibrium, we're saying, what is the deviation from ideal gas behavior? Because it truncates a lot of the complexity and it doesn't impact our phase behavior calculations. So it doesn't impact the math, and it makes the math easier. It's sort of a win-win situation. The downside to it is that we have to add on more and more complexity, more unit definitions, more arbitrary functions, and all this stuff here. But the key thing to remember is that these are all done as a convenience for the calculations. So the end result calculations are actually easier as a result of all of this here. Okay, so as a recap, this is a bit of a sidestep. The fugacity of phase 1 is equal to the fugacity of phase 2, or the fugacity coefficient of phase 1 is equal to the fugacity coefficient of phase 2. For single component systems, no big deal. In the homework, when you're asked to solve for the vapor pressure of a particular fluid using a particular equation of state, you could use fugacities, you could integrate the Gibbs free energies, you could very carefully try and estimate the volumes, right? Whatever your method of procedure is, make sure you can automate it, because for the next homework, you'll have to do it like 50 times. So whatever procedure you're doing to calculate it, you'll have to automate it. But for multi-component systems, then fugacity really shines. It makes the calculations much, much more simple. So if we do a recap then, if we look at our PV diagram for a particular equation of state, again, we've drawn out an isotherm. The temperature is constant. We're going to guess some value here for the vapor pressure. Maybe that's better than last time. So at this point right here, P and T are constant, right? We're following along a path of constant temperature, and we've drawn a horizontal line. We can either match these areas to know that we are in our correct two-phase region, where this pressure is equal to the vapor pressure, which of course will change as a function of temperature. As you increase the temperature, this will of course change, and you will have a new two-phase region. And if we were to plot up the vapor pressure as a function of temperature, it will look exponential, and it will end at the critical point. Now that critical point corresponds to a graph that looks like this, where there is no longer an inflection point. Well, it is an inflection. There's not multiple reflections. Okay, so the next problem, though, is we could also use the fugacity. So in this case here, the fugacity of the vapor has to be equal to the fugacity of the liquid. So I'm going to jump back really quickly to our definition of fugacity. So if we use this bottom equation here for fugacity, the problem is we need to know what volume all of this is going on at. Which means we need to know these volumes here, and getting these involves solving the cubic equation. One other complication. We are going from an ideal gas to a real fluid when we've defined our fugacity. So we've come somewhere from all the way up here at low pressure and high volume. And we've followed along a path of constant temperature, and then we've hit the start of our two-phase region. But the problem is, how does the fugacity behave across the phase transition? Because then we need to calculate our fugacity and derive an equation for the fugacity of a liquid. So we need to go back, revisit our definition of fugacity, and see, well, how does it change when we're trying to calculate the fugacity of a liquid? And from there, now we have some formula that we can hold on to and says, okay, all we have to do is find out the conditions where the fugacity of this equation of the liquid equals the fugacity of this equation as the vapor. And that's what we'll do to finish out the class. Okay, so fugacity of a liquid. So this is obviously important in vapor-liquid equilibrium, but it's also going to be our starting point for liquid-liquid equilibrium. Or we don't talk about it much, but of course it'll be our starting point for solid-liquid equilibrium. In general, the specific volume of a liquid is much, much smaller than the specific volume of a vapor, or we could write this that Z is much, much smaller. Right, so recall that if Z is equal to 1, it's effectively ideal gas behavior. So of course we would expect a liquid to be highly non-ideal. So we would expect massive deviations from 1 for a liquid. So when we defined fugacity, it was a function of this integral, 0 to p of a bunch of complex stuff, dp. Right, and this involves a phase transition. So what we're going to do is we're going to break it into 3 steps. One, we're going to go from the ideal gas state to a saturated vapor. No phase changes involved there, right? We're just pressurizing the system. 2, we're going to go from a saturated vapor to a saturated liquid. And then we're going to take it all the way down to a subcooled liquid. So we have a generalized formula for the fugacity of a liquid. Now for vapor-liquid equilibrium, we don't really care about that much, right? Because obviously we're trying to get the saturated liquid fugacity. But for liquid-liquid equilibrium, you'll be working with subcooled liquids, not saturated liquids. Okay. So we're going to I'm going to use this form of the fugacity just to be convenient. I'm going to break it into the 3 individual steps. So the first step is we're integrating from P equals 0 to the vapor pressure, assuming we know what it is. Okay, so this is step 1. Step 2. And step 3. saturated liquid to a subcooled liquid. So conveniently, this one goes away because the fugacity of a liquid is equal to a fugacity of a vapor at saturation. So there's no change in fugacity across the phase change. This term right here, the first term, this is merely equal to just the saturated liquid fugacity. Sorry, saturated vapor fugacity. No different than the first part of the calculation. And to get it in a common form, we're going to partially integrate the third term in the expression. Okay, so I'm going to skip over some steps and get us to the final conclusion. So what I'm going to do is, if we go back to our beginning starting point, which is here. So at our starting point, our left-hand side of the equation, this is RT-ln. So we're going to divide everything by RT and then take the exponent of everything. Now what the exponent allows us to do is allows us to combine all of these adds into multiplies and divides. So it lets us cancel some things out. So what we'll get out of it is eventually that the fugacity of the liquid is equal to P This P came from the left-hand side of the equation. This came from step 1. This came from step 3. And this term came from step 3. Just to retrace our steps. The saturation pressure is the same thing as the vapor pressure. And obviously, the pressure is the same thing as the pressure. And we get out our final result, the fugacity of a liquid is roughly approximated as just the fugacity of the saturated vapor And we have an additional thing. This term here is called the pointing correction. And this is really only valid for high pressures or low temperatures.
What range is high pressure?
Oh, I would say when you're getting into the 10s, 50s, or hundreds of atmospheres. Fairly significant pressures. Nothing near ambient at all. So what's convenient about this is that if we have an expression to calculate the fugacity of a compound following a particular equation of state, just as we have two intersections, let me draw it out again. If we have an equation where we can calculate the fugacity at every point along this line, then we basically can derive an expression that we can directly analytically solve for the fugacity where the vapor and the liquid are equal, and then we can know what the vapor pressure is. So that's what I would recommend is probably the easiest way to solve vapor-liquid equilibrium using an equation of state. So on the homework, in one of the problems, I don't know, problem X, you'll derive an expression for the fugacity using the van der Waals equation of state, and whatever the next question is, you'll use this expression to do vapor-liquid equilibrium. Then the next homework, you'll take the same procedure and do it over again. Okay, so we have a few more minutes. I'm just going to go over a couple of approximations. So we have an expression here for the fugacity of a liquid, and this is an exact expression. Same thing as I wrote just before. So if we had real experimental data, we could actually just integrate this expression numerically if we had V as a function of P. But in general, liquid, their densities don't change that much as a function of pressure unless you're going to really high pressures, which is why this term is not all that significant. So if we assume that the V is equal to a constant, this is an incompressible approximation, in which case this integral here simplifies to V like this. So we could write out the fugacity of the liquid. Just doing a simplification there. If the vapor is an ideal gas, that means that the pressure is probably reasonably low. The fugacity of the liquid is just equal to the vapor pressure. If you have a non-ideal vapor, but you're still pretty close to the vapor pressure, the fugacity is effectively equal to just the saturated vapor pressure. saturated fugacity. And lastly, this equation here, the one in the middle, you could apply that for liquids or solids. So for solid-liquid equilibrium, you could effectively use the same expression. So in many ways, the difference then between solids and liquids from a thermodynamic perspective is just how does their density change as a function of pressure, if we think about it strictly in terms of fugacity. Because, for example, if we wanted to do solid-liquid, we would use exactly the same expression, that the fugacity of the liquid at some temperature pressure is equal to the fugacity of the solid at some temperature and pressure. So in order to do all phase equilibrium calculations, again, all we really need to know is how P, V, and T relate to one another for all phases, for all compounds. Now this is non-trivial, right? So most all the equations of state that we have, they're all derived empirically. They have some formal foundation, right? So in the van der Waals equations, you've got that B term, which is the excluded volume, and the A term, which counts for interparticle interactions. Right? So they have some basis and foundation in reality, but in terms of how you calculate the A's, how you calculate the B's, they're mostly empirically done. And so in more advanced equations of state, you'll have this term called omega, right, which is the eccentric factor. Now, you read thermodynamic books, and they say, oh, well, the eccentric factor accounts for how non-spherical the particle is. Well, that's not necessarily very true at all. Because if you look at this eccentric factor for CO2, and you compare it to carbon disulfide, so CO2 or carbon disulfide, wow, those both look pretty similar in terms of how asymmetrical they are. They have totally different eccentric factors. So in reality, the eccentric factor here is just a tuning parameter to make the equations of state fit better. But if the equation of state is good enough, we can rely on it to do vapor-liquid equilibrium calculations, or any other type of phase equilibrium we'd like to. So that's why a lot of research is put into accurate predictions of material properties. It's not just to know how big of a tank you need and all that kind of stuff, which is typically what undergraduate students will work on with equations of state. It's really much more powerful than that. Everything you need to know about thermodynamics is contained within an equation of state. Enthalpy, entropy, Gibbs, phase transitions, absolutely everything is all contained within an equation of state. So that's why we really, really care about them. And that's why people spend a lot of time and effort in developing them. All right. Any questions? So please, when I post the homework, take a look at it, and we'll field questions on class on Wednesday and Friday. Friday, there will be a quiz. We'll do it right at the beginning of class. It'll mostly cover everything in homework 1, which means state changes, material properties, energy balances, a little bit of differential calculus, and all that kind of stuff. Right? So be prepared to do derivations, turbines, expanders, compressors, heat exchangers, entropy generation, all that fun stuff. All right. Yes, question?
Oh, when will homework be due?
Homework will do sometime next week. Yeah. So before exam 1, you'll have homeworks 1, 2, and 3. And so exam 1 will cover probably through, it depends how far we get, but into multi-component phase equilibrium. We won't be able to cover all of classical thermodynamics within the exam 1 time period, but we'll try our darndest. Okay. See you guys.